Hello everyone, Mr. Hasty here again. Today we're going to be starting section 7.4, which discusses arc length. We're going to discuss the purpose, definitions, formulas, a proof of those formulas, and a basic example of finding the arc length of a curve. So let's talk about the purpose of this. The purpose of this is if we have any curve, no matter how odd or strange, as long as that curve is smooth and continuous, we want to be able to tell from the some start point to some end point, what is the distance of something traveling along that curve. Now, a useful application for this is that if we have some pathway that we need to know the distance of, and that pathway is not necessarily a straight line, we could apply this method to find that distance. A common application of this is software that does route planning, such as Google Maps. Basically, what it will do is it'll break up a long stretch of terrain into little increments, measuring those distances, and then summing them up. And as you get a more accurate estimate, you would have smaller and smaller segments. And we've gone through this kind of logic before. As they get smaller and smaller, our estimate becomes more and more accurate. And as they get infinitely small, our measurement gets infinitely accurate. And to do that, we use an integral. So let's start with the definition. Arc length is the distance traveled along a curve between 2 points. All right, so let's go in and look at some formulas for this. All right, so our formula for finding arc length can be written in terms of x's or y's. The formulas can be given as for a smooth curve from the points A, C to B, D, the arc length is given by the following formulas. L equals the integral from A to B of the square root of 1 plus the quantity dy over dx squared dx, or from C to D of 1 plus dx over dy, quantity squared dy. And basically what the two formula purposes is the top one would be the one we would use if our formula is in terms of x, if the curve we want to work with is in terms of x. And as you might imagine, dy over dx is the derivative of that function with respect to x. Notice that the bounds are from A to B because our x-coordinates go from A to B in the description. The alternate formula would be for y. If we're going from y value of c to a y value of d, we go from y value of c to y value of d. And this derivative is actually the derivative of x with respect to y. It would just be the reverse of how we normally operate. So let's get into a proof of that. All right, so we're going to go through a series of logical steps. Let's draw a diagram that we can reference. All right. So we have a curve, some nature, and this is our point A comma C, and this is our point B comma D. So we've talked about the logic already a little bit. If we drew a straight line between these points, we could measure the distance of that straight line, but it would not necessarily be a good approximation. But let's start there. A long time ago, we learned the distance formula. Distance equals the square root of x2 minus x1 squared plus the quantity y2 minus y1 squared. Now, at the beginning of calculus, we talked about x2 minus x1 and y2 minus y1. We gave those new names to make it easier. We called them delta x and delta y. So if we had one straight line, that's how we'd find the distance. But we already know that our basic approach is to make a lot of little straight lines along the way. So what we're doing is we're essentially summing up many small distance formulas. So we'll call that big D, or L, actually. So what we're doing is we're taking the summation of all those little regions, if we did it a bunch of times. Now, we're doing this on a specific interval. We're doing this for purposes of the proof for x, a to b. Now, if you remember back, this is starting to look like the original definition of an integral that we did. What's missing here? Particularly in the definition of an integral, right here, we would have a delta x, which would translate into our dx. So we're going to have to do some algebraic work here to get that delta x out. And we're doing that purely to make this into the form of an integral. So what I'm going to do is underneath my square root, I'm going to factor out a delta x squared. Now, when you factor out a delta x squared from delta x squared, you get 1. When you factor out a delta x squared from a delta y, you're going to get delta y squared divided by delta x squared. Now, that's going to result in having a delta x squared inside of your radical, but outside of the quantity you just made. And this is still on the interval a to b. Now, let's make sure we're okay with that. That delta x squared, if we were to distribute it back in, would cancel out the delta x squared on the bottom, leaving us with delta y squared. And if we take delta x squared times 1, we get delta x squared. It is the same expression, just rewritten. Now, if we have delta x squared inside of our radical, we can translate that into a delta x outside of our radical. I'm also going to do a brief simplification here. Delta y squared and delta x squared as a quotient can be simplified using exponent rules as delta x over delta y quantity squared. still on a to b. And now this looks almost exactly like when we translated summations into integrals. This would be the integral. Because we're on the interval a to b, it's from a to b, square root. Now we typically do not use delta notations in an integral. We change that to dx, or I flipped them here. Let me fix that. So got that fixed. And our delta x would be a dx. And that's the formula we were given at the beginning. So real quick, let's move on to one example. What is the length of one period of a sine curve? So let's go into Desmos and look at a picture of a sine curve. This is our standard sine curve here. And if we look, one period is from any given point to the exact same point similarity. So we could say from 0, 0 to 2 pi comma 0. That would be one period. That's the standard period we typically refer to as a sine curve. And what we're finding here is we're finding the distance as we go along that curve. So what that means? Our function is y equals sine x. So if we're going to use this formula, we need to establish two things. Number one, what is our bounds? And what is our derivative? Well, our derivative is simply if y equals sine x, dy over dx is cosine x. And because we're doing one period of the sine curve, we just discussed how one period would be from 0 to 2 pi. So our integral is simply from 0 to 2 pi of root 1 plus cosine squared x. And again, the squared on the cosine comes from the squared in the formula, dx. Now, doing this one by hand is a bit challenging, so we would just turn to the calculator and get approximately 7.640. In this case, if we wanted to include some form of units, it'd just be units because we're finding a distance, not like a area or a volume. I'm going to make another video later that goes over some of the more challenging examples and how to do some of these more tricky integrals by hand instead of relying on the calculator. But that'll be for next time. See ya.